Hello everyone. Today we're diving deep into the fascinating realm of lexical structure in programming languages, particularly focusing on the intriguing world of Python. Get ready for a ride that will not only demystify the fundamental rules that govern how we write code, but also reveal the hidden humor and connections to pop culture that lie beneath the surface. Now, before we embark on this journey, I want you to imagine that the Python programming language is like the main character in a movie. You see, just like a movie character has certain quirks and behaviors that make them unique, Python has its own set of lexical rules that define its personality. These rules are collectively known as the lexical structure of the language, and they govern how we interact with Python on a textual level. Think of it this way. When you write a Python program, you're creating a script for Python's performance. And just like a movie script has specific formatting and rules, a Python program has its lexical structure that dictates how it should be written. It's like Python's way of saying, "Hey, here's how I want you to talk to me." Let's start with a classic example from the world of movies. You know how characters in movies have specific names that reflect their identity? Well, in Python, variables also have names, and these names are governed by the lexical rules. Imagine if your favorite movie character had a name that was just a bunch of random characters. It would be quite confusing, right? Similarly, Python's lexical rules ensure that variable names are meaningful and consistent, making your code easy to understand. Speaking of movies, imagine a scene in a film where the characters are having a conversation. Lines of dialogue are often separated by new lines, right? In Python, lines of code are like lines of dialogue, and they are separated by new lines too. But here's the fun twist. Python is a stickler for neatness and indentation. It's like the grammar police of the programming world. You can't just write code all willy-nilly. You need to pay attention to the layout. If you're coming from another programming language, it's like adapting to a new country's customs. You got to pay attention to the local etiquette. Now, let's take a detour to the world of superheroes. Imagine a superhero with a sidekick who always wears a particular symbol, say a cape. That symbol helps you identify the sidekick, right? Well, in Python, the hash symbol serves as a comment. It's like the superhero's cape, helping you understand the context or purpose of a line of code. Python ignores whatever comes after the hash symbol, treating it as a comment. So next time you see a hash in your code, think of it as the programmer's way of saying, "Hey, here's what's happening." Remember those times in movies when a character has to deliver a really long monologue? Sometimes the monologue is so long that it spans multiple lines. In Python, we have triple-quoted strings that allow us to write long text across multiple lines. It's like giving your code room to breathe. Think of it as the director's cut version of your code. More space to explain yourself. Alright, let's switch gears and talk about something that's been in the news a lot lately. Tabs versus spaces. In Python, indentation matters a lot. It's like the rhythm of your code. Just like in music, the right rhythm can make a melody beautiful, and in Python, the right indentation can make your code elegant. But here's the twist. Python is very clear about its preference. It prefers spaces over tabs. It's like having a favorite instrument in a band. So when you're writing Python code, remember, spaces are the rock stars here. Imagine if you were writing a story and decided to mix up different languages in a single sentence. It might sound cool, but it could also lead to confusion. In Python, mixing tabs and spaces for indentation is a no-no. It's like trying to tell a story in multiple languages all at once. It's going to be hard to follow. Python wants you to pick one and stick with it. So, it's a good idea to configure your text editor to use spaces for consistency. Alright, now let's bring in a classic movie trope, the hero who's always giving advice. In Python, we have some built-in advice in the form of keywords. Think of these keywords as the sage advice from a mentor character. They're like the magic words that tell Python what you want to do. Just like characters in movies follow certain rules, Python's keywords guide the flow of your code. Now here's where things get interesting. You know how some characters in movies have secret abilities? Well, Python's keywords have some secret tricks too. For instance, the AND keyword can help you combine conditions, like a superhero team-up. And then there's if, a keyword that helps your code make decisions, like a character choosing between two paths. Let's take a moment to dive into a conspiracy theory that involves Python programming and its fundamental concepts. This theory suggests that Python's way of handling variables and references is more than just a programming language feature. It's a reflection of how our reality might be structured. Imagine a world where our reality is just a vast, complex program, and everything we experience is merely the result of references being bound to objects. In Python, a reference is like a name that connects us to the objects in our surroundings. It's intriguing to think that variables in Python represent the various elements of our existence, and by rebinding those variables, we could potentially reshape reality itself. Consider the idea that just like Python variables can be global or local, there might be global and local aspects to our reality. Could our planet be a local reference within the global universe, all controlled by some cosmic Python interpreter? Attributes and items in Python's objects could parallel the attributes and elements of our world. Our physical properties and characteristics could be seen as attributes of a larger object, our planet. The elements around us, such as trees, animals, and objects, might be the items within this larger container. Accessing non-existent references in Python is akin to facing existential questions in life. What happens when we try to access something that doesn't exist? Could it be that certain mysteries or phenomena we can't explain are simply due to accessing non-existent references in our reality's code? The assignment statements in Python could be symbolic representations of how changes occur in our existence. When we learn something new, is it like assigning a new value to an existing variable in the cosmic Python program? Augmented assignments might be more than just programming shorthand. They could represent how our intentions and actions modify the world around us. By taking certain actions, we could be augmenting the state of our reality, just like augmenting assignments modify variables in Python. Del statements could signify the end of certain aspects of reality. When something is deleted, it doesn't necessarily disappear entirely. It might just be unbound from our reference. Similarly, when people or things leave our lives, they're not erased. They're just unbound from our personal references. The concept of expressions and operators could relate to how we make sense of our world. We build our understanding through expressions, combining sub-expressions with operators to evaluate the truth value of our surroundings. Comparison chaining in Python is reminiscent of how we build up our beliefs and judgments based on the comparison of experiences. We form a logical chain of thoughts, just like chaining comparisons to deduce truths. The idea of short-circuiting operators aligns with how we make quick decisions in life. Sometimes we don't need to evaluate everything to reach a conclusion. We rely on shortcuts to navigate the complexities of existence. Intriguingly, the conditional operator in Python is similar to how we often make choices based on conditions and outcomes. If we choose one path, we experience one outcome. If we choose another, we experience a different outcome. Assignment expressions could be seen as a metaphor for making choices that alter the course of our lives. Each choice we make could be an assignment to our reality, determining the value of our experiences. As intriguing and imaginative as these connections may be, it's important to remember that this conspiracy theory is pure speculation and doesn't have any scientific basis. Python's programming concepts are designed to help us understand and manipulate computer programs, not to describe the fundamental nature of reality. While drawing parallels between programming and reality can be thought-provoking, it's essential to maintain a clear distinction between the two domains. Ladies and gentlemen, distinguished scholars and curious minds, I welcome you to this enlightening lecture on the intricate concepts of sequences, iterables, and various data structures in Python. Our journey through this intricate landscape will take us to the depths of strings, bytes, tuples, lists, sets, and dictionaries, unraveling their true nature and the role they play in the Python programming world. Sequences and iterables, a foundation. Let us embark upon this exploration with sequences, the ordered containers of items indexed by integers. Python's arsenal of sequence types, strings, tuples, and lists, form the cornerstone of these ordered collections. These sequences allow us to manipulate and interact with data in a structured manner. We must also acknowledge that extensions and libraries expand this collection to encompass additional sequence types, opening the doors for further customization and versatility. At the core of Python's iteration behavior lies the concept of iterables. The ability to traverse sequences or collections is fundamental to programming, and iterables capture this behavior abstractly. Every sequence can be iterated over, be it a string, a list, or any other sequence type. However, caution is necessary when dealing with unbounded iterables, as they can potentially lead to never-ending processes or resource exhaustion. Strings, unraveling textual information strings. Those enigmatic containers of textual information come in two forms, str and bytes. Str objects serve as sequences of characters, housing textual data. Meanwhile, bytes objects accommodate arbitrary binary data sequences. Immutability characterizes both string types, ensuring that operations on strings generate new string objects rather than modifying existing ones. Delving into string literals, we explore the realm of single and double quotes. Both function identically, enabling us to include one kind of quote within a string specified by the other. Triple quoted strings offer a haven for multi-line content, preserving new lines as new line characters within the resulting string object. Using an escape new line as the starting point provides a clean solution to maintain consistent indentation. Understanding escape sequences, those intricate patterns of characters, enables us to introduce special characters within string literals. From new line characters to Unicode characters, these escape sequences empower us to craft rich and diverse textual content within our code. Bytes and byte arrays, navigating binary realms. Bytes objects, the guardians of binary sequences, hold a range of integers from 0 to 255. In scenarios where binary data from files, sockets, or networks needs handling, bytes objects come to our rescue. We initialize bytes objects from integer sequences or character strings. Mutable cousins of bytes, byte array objects, facilitate modifications within the sequence of byte values. The ability to alter individual elements adds a layer of flexibility not seen in bytes objects. Converting between bytes and strings is a task made simple with the decode and encode methods, which effortlessly shuttle between these two worlds. Tuples and lists, immutable and mutable sequences. Tuples, the immutable ordered sequences, hold a diverse array of items. While tuples can house mutable objects, best practices often steer us away from this approach. Denoting tuples involves comma-separated expressions enclosed in parentheses, with optional redundant commas at the end. We can create tuples through literals or by invoking the built-in tuple function. In contrast, lists, the mutable siblings of tuples, facilitate modifications and adjustments to sequences. Literal list notation involves expressions enclosed in square brackets, similar to tuple notation. Lists can house items of varying types, but the central notion remains: sequences we can manipulate at will. Just like tuples, we can create lists through literals or by calling the list function. Sets, embracing uniqueness and unorderliness. Python's set types, set and frozen set, captivate our imagination by organizing unique items in arbitrary order. Hashable objects are key players in sets, ensuring efficient data storage and retrieval. While sets are mutable, frozen sets stand as their immutable counterparts. Sets spring forth from braces, with items separated by commas. This intuitive structure accommodates various item types, fostering the creation of diverse and powerful data structures. Whether it's the mutable set or its immutable counterpart, the essence of these collections lies in their ability to hold distinct items while remaining unordered. Dictionaries. Mapping the unmapped mapping, the art of associating values with keys, finds its epitome in Python's dictionary type, dict. Dictionaries take on the role of associative arrays, enabling us to access values using keys. Each key is unique, and dictionaries do not support duplicate keys. Welcome to this whimsical yet enlightening lecture, where we'll explore the realm of Python's type annotations, the enigmatic MyPy, and a cast of other intriguing characters that have joined the Python ecosystem. Part 1. The mysterious MyPy. In the enchanting land of Python, type annotations have become as common as enchanted potions in a wizard's chamber. And with these annotations, enter our first protagonist, MyPy, the stalwart guardian of static type checking. Just like a wizard's trusty spellbook, MyPy keeps evolving alongside Python's type annotation forms. It's a utility that peers into your code, checking types with unswerving diligence. But that's not all. MyPy is like a shape-shifting sorcerer, adapting to different editors and IDEs like Vim, PyCharm, and even the elusive Atom. To summon MyPy's magic, you chant the spell, MyPy my Python script.py. But don't worry, we won't leave you spellbound. Detailed usage examples and a cheat sheet await in the MyPy online documentation, a treasure trove of knowledge to aid your journey. Part 2. The Curious Crew. As the tale unfolds, we introduce you to a motley crew of other type checkers, Monkey Type, a mischievous companion who dynamically detects types at runtime, generating .py, stub, files. It's like a playful spirit that dances with your code's essence. Pedantic. This quirky character focuses on ensuring your Python code receives only the purest data, a true guardian of cleanliness in the code realm. Pylance. Imagine Pylance as the stylish trendsetter who embeds Pyrite into VS Code. It's like Pyrite's fashionable alter ego, making type checking a runway show. Pyre. A mystical sage from Facebook's realm, Pyre can craft PII files, but prefers the company of Linux. It's like a hermit with profound wisdom to share. Pyrite. Microsoft's artisanal creation, Pyrite dons the hats of both a command line tool and a VS Code extension. It's the vigilant protector of your code's integrity. PyType. PyType, the enigmatic seer from Google's domain. It peers into code's depths, inferring types even in the absence of explicit hints, and it shapes PII files like a skilled potter at work. Part 3. Unraveling the mystical syntax. In this chapter of our tale, we delve into the secrets of type annotation syntax. It's like deciphering ancient runes, an identifier followed by a type specification, a dance between names and their arcane natures. But wait, there's more. Python 3.9 and 3.10 bring forth changes that spark intrigue. Python 3.9 welcomes built-in types with open arms, while Python 3.10 introduces the vertical bar operator to signify alternative types, a language upgrade akin to a secret code that only the initiated can decipher. Part 4. The Typing Chronicles. The epic saga of the typing module. It's a realm of classes and functions that define, modify, and transcend types. This is where the arcane meets the practical. Any, a wildcard that embraces all types, as if casting a wide net into the unknown. Any star, a fusion of strings and bytes, a harmonious duet in the symphony of data. Binary I/O, streams that bear the mark of bytes like rivers of binary information. Callable, a signature of function mastery, akin to a key that unlocks code's hidden potential. And there's more, a cavalcade of types and expressions that paints a vibrant tapestry of possibilities. Epilogue. The Pioneers of Protocols. Before the final curtain falls, we glimpse into the realm of protocols. These aren't just rules, they're like the unwritten laws of a secret society. Protocols, abstract base classes with a touch of wizardry, they express constraints on a type like riddles that reveal a class's abilities. As the stars begin to twinkle in the evening sky, we conclude our tale of type-checking utilities, a tale of enchantment, mystery, and a touch of the unexpected. Remember, fellow adventurers, that in Python's world, type annotations are not just annotations, they're the incantations that bring clarity, order, and magic to your code. And so, dear travelers, may your code be ever precise, your types be well checked, and your programming journey always filled with wonder and discovery. Intermission. The enchanted journey continues. As we step into the next chapter of our enchanted journey through the world of Python's type-checking utilities, let us explore deeper into the heart of type annotations, uncovering the intricacies of syntax, and delving into the very essence of the typing module's offerings. Part 5. Syntax Unveiled. In the dimly lit corridors of code, syntax is the lantern that guides us. But fear not, for the syntax of type annotations is not a labyrinth, but a path paved with clarity. A type annotation follows the pattern of identifier, type_specification, a dance between names and their intrinsic natures. Imagine it as a map, leading you to the treasure trove of information hidden within your code. Ladies and gentlemen, today's lecture will delve into the topic of exceptions in Python, with a focus on OSERA subclasses, handling exceptions, and error-checking strategies. So, let's get started. OSERA subclasses. OSERA, a fundamental class in Python, is used to represent errors detected by the operating system. To make error handling more refined, Python provides various subclasses of OSERA. These subclasses are raised in specific situations, enabling us to handle errors more elegantly. You can find a comprehensive list of these subclasses in Python's official documentation. For instance, consider a common task, reading and returning the contents of a file, returning a default string if the file does not exist, and propagating any other exceptions that make the file unreadable. The FileNotFoundError subclass of OSERA simplifies this task. Python, copycode def read or default, filepath default, try, with open filepath, as f, return frred, except FileNotFoundError, return default exception. Chaining and wrapping Python allows exceptions to be wrapped or chained together. This means that when an exception occurs during exception handling, the original exception is preserved, and a new one can be raised along with the original context. Python's error messages provide details from both the original exception and the intervening one. By using the raise from statement, you can control the display of these chained exceptions. For example, when one exception occurs during the handling of another, Python copycode, try, 1, 0, except 0 division, error, 1 plus nx. Python displays both exceptions, Arduino copycode, traceback, most recent call last, file, line 1 in 0 division error, division by 0. During handling of the above exception, another exception occurred, traceback, most recent call last, file, line 3 in type error, unsupported operand types, for plus, int and str custom exception classes. Python allows you to create your own exception classes by extending standard exception classes. This practice enables you to define your own exceptions with specific meanings for your applications. Custom exceptions enhance code readability and help distinguish different error scenarios. Python copycode class, invalid attribute error, used to indicate attributes that could never be valid. Using custom exception classes allows you to handle specific error cases more effectively. You can catch these exceptions separately, which makes your code clearer and more maintainable. Error checking strategies. LBYL versus EAFP. Python promotes the easier-to-ask forgiveness than permission. EAFP, error handling strategy over the look before you leap, LBYL strategy. EAFP encourages you to attempt an operation and handle exceptions that may arise, rather than checking conditions beforehand. EAFP is more readable and avoids duplicating code, making your program more robust and less prone to errors. However, care must be taken not to catch too broad a range of exceptions, potentially hiding unexpected issues. Logging errors and exception. Reporting Python provides ways to handle unhandled exceptions and report errors. You can redirect error messages to a custom stream by rebinding sys.stdr. Additionally, you can customize exception reporting by assigning your own function to sys_except_hook, which gets called when the program terminates due to an unhandled exception. This function can format and direct exception information for analysis and debugging purposes. Conclusion. In this lecture, we explored various aspects of exceptions in Python. We discussed how OSERA subclasses can streamline error handling, the concept of exception chaining and wrapping, creating custom exception classes for more expressive error handling, and the strategies of LBYL and EAFP for error checking. We also touched on error logging and exception reporting to enhance debugging and diagnosis. Exception handling is a crucial aspect of writing reliable and maintainable Python code. Handling multiple exceptions, exception group and except. Python 3.11 introduced a mechanism to raise and handle multiple exceptions at once, using the exception group class and the except form. This is particularly useful when validating data against multiple criteria. Python exception handling and context managers. Good day, everyone. In today's lecture, we'll delve into the intricate world of exception handling in Python, exploring how exceptions are used to indicate errors and anomalies within your code. We'll also uncover the power of context managers, which help manage resources and ensure proper cleanup in your programs. So, without further ado, let's embark on this informative journey. 1. Introduction to exceptions. In Python, exceptions are used to signal errors and anomalies. When an error is detected, Python raises an exception, effectively notifying the occurrence of an unexpected condition. This exception is then propagated through the code using a mechanism that passes along an exception object. Exceptions can be categorized into two types. Built-in exceptions. These are predefined exceptions provided by Python. Examples include value error, type error, and zero division error. Custom exceptions. You can also define your own exception classes by inheriting from the base exception class or its subclasses. This is particularly useful when your code needs to communicate specific error scenarios. Let's move on to understand how exception handling works in Python. 2. Handling exceptions. Exception handling involves catching exceptions and taking appropriate actions to manage the unexpected condition. If an exception is not handled, your program terminates and displays an error message along with a traceback. The try statement is the core of exception handling in Python. It consists of three optional clauses. Try, the block of code where an exception might occur. Except, one or more clauses that define how to handle specific exceptions. Finally, an optional clause that is always executed, regardless of whether an exception was raised or not. Here's the basic structure of a try statement. Python copy code. Try, hash code that might raise an exception except, expression as target. Hash code to handle the exception, else, hash code to execute if no exceptions were raised. Finally, hash cleanup code that always executes. The except clause catches exceptions based on specified conditions, expressions, and executes the corresponding code block. If no exceptions occur, the else clause's code is executed. The finally clause is used for cleanup, ensuring that resources are released even in the presence of exceptions. 3. Exception propagation. Exception propagation refers to the process by which an exception travels up the call stack until it finds a suitable exception handler. The first matching except clause is executed, and if none are found, the program terminates. It's crucial to place handlers for specific exceptions before more general ones to ensure that the correct handler is executed. Avoid using a bare except, an except clause without an expression, unless you're re-raising the exception, as it can hide coding errors and interfere with process exiting exceptions. 4. The raise statement. The raise statement allows you to raise exceptions explicitly. It can be used with or without an expression. When used without an expression, it re-raises the exception being handled. You can also include the from keyword to create a chain of exceptions. Example, Python copy code. Try, value equals sign 10 except zero division error, raise value error, caught divide by zero attempt, from none 5. Context managers. Context managers, provided by the with statement, ensure proper setup and cleanup of resources. They allow you to manage resources like files, network connections, or database connections conveniently. Context managers are created by defining classes with __, enter __, and __exit methods. The __, enter __, method initializes resources, while the __, exit method handles cleanup. Python's context_lib module provides a decorator to create context managers using generator functions. Python copy code, eContextLib, context manager, def enclosing tag, tagname, print for tagname, end =, try, yield finally, print of tagname. 6. Exception, handling with generators. Generators can cooperate with exceptions by using the yield statement inside, try and finally blocks. Generators have methods like throw and close to interact with exceptions. 7. Exception, propagation and handling hierarchies. Exceptions propagate upward in the call stack until a suitable handler is found. It's important to design your exception handling to ensure the correct handler is reached. Placing specific exception handlers before general ones is a good practice. 8. Conclusion. In conclusion, mastering exception handling and context managers is essential for writing robust and reliable Python code. By understanding how to handle exceptions, you can gracefully manage unexpected conditions, preventing your programs from crashing. Context managers, on the other hand, ensure resources are properly managed and cleaned up, contributing to efficient and safe code execution.